15 days, we will think what we are doing. We have not started it. We have not started. We just have prepared timetable only. Now how many days are there, ma'am? Now how many days are there? 15 days. Okay? 15 days, how many subjects are there? 6 subjects. Each subject will get 2 days. 6 2s are 12. First subject 3 days once again. Correct or not? This is how we plan, no? First subject 3 days. 1 week over we have not started. Okay? So how many days are there? 7 days. How many subjects are there? No problem. 6 subjects, 6 days. Last day, first subject. Correct or not? Yes. We do this or not? Over. Tomorrow is exam. Not started. Not started. No problem. 24 hours are there. 6 hours for sleeping. So how many hours are there? 18 hours are there. How many units are there? 5 units are there. 5 3s are 15. Each unit 3 hours. Okay. 3 hours. Good. Okay, 3 hours food, dinner. Evening 6 o'clock, you have not started the preparation. Immediately, you will call to your friend, hey, important questions. Important questions. Right? So, 6 o'clock, we will try to read important questions. Then you tell me, where is the time for us to understand the subject? Yes? We are just planning to write the examination. This is what we are doing in semester pattern. Then there is a chance for us to think about the subject. Got my point? So this is about intelligent cycling. Now you see, planning is there. We are very good planners. Collection is there. We collect all the material from all the branches if it is necessary also. Seniors, super seniors, all the material we will be having. Collection, no problem. Processing, we do very good processing also, right? Very good planning, everything. Where we have analysis also. Long answer question, short answer question, 2 marks question, all the question bank will be having, no? Analysis also there. What is missing here? Dissemination. 6 hours for sleeping. So how many hours are there? 18 hours are there. How many units are there? 5 units are there. 5 3s are 15. Each unit 3 hours. Okay. 3 hours food. Okay? 3 hours food. Dinner. Evening 6 o'clock, you have not started the preparation. Immediately, you will call to your friend, hey, important questions. Tell me some important questions. Right? So, 6 o'clock, we will try to read important questions. Then you tell me, where is the time for us to understand the subject? Yes? We are just planning to write the examination. This is what we are doing in semester pattern. Then there is a chance for us to think about the subject. Got my point? So this is about intelligent cycling. Now you see, planning is there. We are very good planners. Collection is there. We collect all the material from all the branches if it is necessary also. Seniors, super seniors, all the material we will be having. Collection, no problem. Processing, we do very good processing also, right? Very good planning, everything. Where we have analysis also. Long answer question, short answer question, 2 marks question, all the question bank will be having, no? Analysis also there. What is missing here? Dissemination. What is missing? Execution is missing. Execution is missing. Having come to this class and having listening a different kind of experience in the process of learning, still if you are feeling 1 or 2 times that, no, I am not getting into the groove of the class, please think in this 15 minutes break. That means you are not in the process of dissemination. Come back after the break with interest. We will see how it goes hereafter. Thank you. There is an ant. The ant is sitting on a water droplet. Yes? A small ant sitting on a water droplet. What do you mean about it? Actually, if I have internet, I could have run this link for you. It is nothing but an ant swimming over a water droplet. So what I am trying to say is, this intelligence processing is taking us in such a way where able to perform certain calculations about the amount of pressure that is exerted by these legs of hand on the water droplet. Even that pressure also we can calculate using the computational engineering. Right? So the amount of pressure exerted by the hand on the water droplet can also be calculated. The reason for the hand to float on the water and not, but if you want to walk on the water, whether it is possible? If you want to walk on the water, is it possible for you? Not. But for hand, why it is possible? You say simply mass. Right? Then it is not only mass, there is an equation which governs us. The equation is next. What is the equation? F equals x. So I discussed from morning many issues, right? These many issues are there. We bundle them, all of them. When you bundle, what happens? It is just like a I am an engineer, I want a proof. Yes? We enjoy the bike ride now. Bike ride. Right? When you are just riding a bike on the road, normally what you will get? A speed breaker. So when you have the speed breaker, what you will do? You will raise the accelerator or lower the accelerator? Lower the accelerator. Very good. Sir, I don't have bike, sir. I have a ladybird license. Okay? So I am just going on a ladybird license. So when I am passing through, I have some sand. Right? Somebody is constructing a house. In our towns, normally we pour it on the main road. Right? We don't have the discipline of making it to the other side of the road. So when the sand is poured on the road, having seen that portion of sand, whether a person riding this cycle turns back or will want to proceed further. Generally, we'll go ahead. Yes, we'll go ahead, but this time in the sandy portion, we'll spend more energy to cross the sandy path. Is it correct or not? So, last 2-3 minutes what I have been talking about is just about nature. Yes, just about nature only. Am I talking anything related to electronics? No, just what is going in daily life I am speaking. Now you see, instead of bike or bicycle, think like an electric current is passing. Right? Instead of bike or bicycle, now this time electric current is passing. Instead of sand, imagine that there is a resistance. Right? So electric current is passing, there is a resistance. When the sand encountered, what you have done, you spend more energy on raising the accelerator, so more fuel is spent, and then you cross the sandy path. Am I correct or not? That means, when there is a resistance, what is spent there? Energy is spent. Am I correct or not? Just to convert that example into electronics. So there is a bike, there is an electric current. There is a sandy path, there is a resistance. There is an energy drop, there is an energy drop. What is this energy drop? Voltage drop. What do you call it as? From this discussion only, V is equal to IR can be explained. What is V equals to IR? Ohm's law. So we can study Ohm's law even in this way also. Yes? So instead of reading the definition just like Ohm's law is nothing but the amount of electric current that would pass through a conductor when certain voltage is applied across it ends. Instead of studying like this, the more energy that you apply, the more faster that you can pass through this particular portion of the sand. That's all. V is directly proportional to I. V is equal to IR. Yes. Exactly same concept is taken in VLSI also. Right? VLSI, if resistor is there, means this resistor is not fabricated as such. What they do, you know? So I have an electric current. So I have a conducting path. So first what they do? They lay down a conducting path. After that sand, non-conducting path. After that again, conducting path. That means one conducting path, one conducting path. In between what we have? Non-conducting path. Can I have a marker? No problem. So we have no issue here. So between two conducting parts, we have one non-conducting part. If you want to find, this is nothing but resistor in VLSI. So how you fabricate resistor? You don't actually make a normal composition resistor or a wire wound resistor. You will lay down a conducting part, after that one non-conducting part, again one conducting part. That particular portion offers some resistance. Right? This is how the application of resistor takes place in using VLSI technology. Understand now? That is, from nature we can discuss about electronics. So every answer of electronics or any, for that matter, any branch of engineering lies in nature only. Understand? We need not search anywhere. Next. We don't discuss about mother, we talk about father. Yes? Nobody talks about even mother of India also. They say father of India. Who is father of India? Huh? People say Mahatma Gandhi, right? So in every branch, father, we say only father. I don't know why we don't talk about mother. Mother is reason for everything, no? For existence, sad. So here also we discuss about one father only. What is that? Father E. More. What is the father name here? The father of VLSI technology is Father E. The interesting aspect of Gordon Moore is he is a founder of Intel. He is a founder of Intel Corporation. Intel processors you are seeing, right? The Intel Corporation is Gordon Moore. Gordon Moore and his friend Robert Noyce has found the Intel Corporation. Robert Noyce has proposed an interesting aspect in VLSI. Normally, if you want to connect one component to another component, what you will do? You will take a wire. Yes, you will take a wire and connect. When you take a wire and connect, if many connections are there, have you done this digital experiment anytime in lab? Digital encoder, decoder, multiplexer. Once after seeing the breadboard, no, it is just like almost a very big hair, right? A zigzag hair, uncombed hair. It looks like. If some output is not coming out, you ask lab assistant to come and that means you will remove everything. Yes, he will remove everything, again he will connect. Why again he has to connect? He can correct what is there exactly, no, it's not possible. The reason is, the connections are so clumsy. Yes, that means when you use wires, in a complex circuit, the connections may be like a traffic junction. Yes, so we need to find an alternative. Then Robert Noyce has proposed a concept called as VIA, V-I-A. What is that? VIA. Instead of wire, what he has used? VIA. VIA means it acts like a wire, but it is within the design. It is not outside the design. Understand? Within the design in the sense, for example, I am asking one student to other student, just hold their hands like this. When they hold the hands, it makes a chain. Yes? It makes a chain, no? So instead of that, if I give a rope and ask them to use, rope is external. Rope is external connection. That also makes a chain. That means it is internal. This is an internal chain. If I use a rope, it is an external chain, external link. So instead of giving external link, internal things are used for providing the connection. This is called as VIA. I show the VIA in the picture, then it will be more clear. Right? For this matter, just you write down a definition like VIA is nothing but an electrical connection that comes within the circuit. Okay, it is not external to the circuit. Understand? Yes. Next. VLSI is needed. Yes. Many wondering question why VLSI? VLSI is very, very essential because of these reasons. What are the reasons? Higher speed, lesser power consumption, lesser area. What are the advantages that VLSI offer for us? Higher speed, lesser area, lesser power consumption. Lesser power consumption means you have a servant now. Okay? Servant will take only one glass of milk. Servant takes only one glass of milk and works for long time. Right? And there is another type of person who takes lot of input, he sleeps for long time. Understand? Two types of servants are there. One servant takes less food, works for long time. The other servant takes more food, ultimately gets the sleep. think here also one or two students, if they are sleeping, it means that they might have taken dosa more in the morning. And so more food and actually it gives you more sleep. I tell you an interesting aspect here is Thevenin's theorem, you know? Thevenin's theorem. How many of you know? Huh? If you make it faster, we learn some new concept. How many of you know Thevenin's theorem? Yes. Please stand and say the statement of Thevenin's theorem. Fastly. Yes? Yes? Fastly. Nobody wants to put themselves in hot soup, right? So nobody wants to stand in an auditorium, but very good. If you ask suddenly these questions in electronics, right? It's difficult to answer. But after listening to this example, you will see how simple it is to understand and remember electronics or VLSI. I tell you here, VLSI in Mahabharata. What is that? VLSI in Mahabharata. The VLSI and electronics are there in Mahabharata. Will you agree with me? Huh? If Mahabharata is a story or reality, we don't know about it, right? We take it now as a story, just like another movie, right? You take Mahabharata story. In that I tell you one incident, you will agree with me that yes, the electronics is there in Mahabharata, VLSI is there from Mahabharata, right? In Mahabharata, one hero is there, hero group is there, villain group is there. What is the hero's group? Pandava. And villains group? Who said that they are villains? Huh? The story portrayed them like this, right? So we have heroes group as well as villains group. One from heroes group like Arjuna will come, right? And the other from this, Duryodhana. These two people will go for seeking help from a person called as Krishna. Yes? From an individual called as Krishna. That is not getting to the details rather. Krishna is not, that is not related to us. We take characters only. We take one character called as Krishna, two other characters called as Duryodhana as well as Arjuna. What happened? Arjuna went there and asked one boon from him. What? You just be with me, I will win the war. Duryodhana, I need all your weapons, horses, etc., etc., give them to me. Yes? Now, I ask you a simple question. The girl is smiling, right? She smelled the answer. In my opinion, Arjuna may be an electronics student. In my opinion, what I am saying, Arjuna may be an electronics student and Duryodhana is an art student. Why sir, why you are saying like this? Being an electronics student only, he knows how to apply Thevenin's theorem. Yes? I imagine like this, that he applied Thevenin's theorem in choosing the search, the Krishna. Right? Arjuna being an electron, that is what intelligence is all about. One more example of intelligence I am saying. Listening is important. Listening is something everybody will do. But applying is something only rarely comes out. Yes? So Arjuna also listened just like any other student of electronics classroom, but he applied when it is needed. That is why it is intelligent choice. How he applied what Thevenin's theorem is, instead of many energy sources, many impedances, one single equivalent open circuit voltage in series with impedance will do the job. Impedance or not, provided all the internal impedances are replaced by equivalent values. That means instead of many weapons, horses, artillery, soldiers, one single person will do the job. Application of Thevenin's theorem or not? Yes. Instead of many circuitry, etc., etc., one so-called monolithic IC will do the job. Is it not the VLSI or not? Yes. So this knowledge probably the student have applied. This student, Arjuna, when Arjuna can apply, why can't you and me apply this? Yes. I will tell one more step ahead. I will say, even Duryodhana is not an art student also. Illiterate. Why sir? If he is an art student now, he knows economics. Economics means how much expense it will take to feed all the horses and all. More money now. But this time with 1 glass of milk, with which I have started my class. 1 glass of milk will do the job. Less input, more work. Whereas more input, less work. Understand? So this is how we can relate the concepts in electronics to different things which we have already studied. Now Thevenin's theorem, example, everybody will say now. Now what is Thevenin's theorem? Instead of many, we can equate it to single equivalent. That's all. Many to one. Many to one what? It's a mathematics function. Right? So mathematics is there, electronics is there, but we unfortunately studied there only electronics. Got my point? Next slide. Now, so before VLSI what we have? Before VLSI we have SSI, small scale integration, MSI, medium scale integration, LSI, large scale integration. The example of large scale integration is 8085 microprocessor. First chip using large scale integration which was developed is 8085 microprocessor, and then VLSI. Next to VLSI we have another technology called GLSI, Giant Large Scale Integration Technology. Yes, next. Origins of VLSI. VLSI concept started, so in the slide they mentioned that it is from 1940, but it started even in the 18th century. There is a physicist called as Fick, F-I-C-K, Fick. A Fick has given an equation called diffusion equation. From that concept the physics of VLSI has started. You know what is diffusion? Diffusion means we are in an auditorium, suddenly one person enters and he sprayed some kind of scent. Okay? So within 1 minute, the fragrance of scent can be experienced by everyone in the auditorium. Am I correct or not? This is called as diffusion. What is this? So instead of saying like this, if I say diffusion is nothing but the phenomenon of spreading up higher concentration region to the lower concentration, nobody will understand. Yes? What something like a rain, this guy is saying, I don't understand what is diffusion. We say in different way. Now, diffusion is nothing but spreading. When it spreads, wherever it is there, from that point, wherever it is not there, there it spreads. Water goes from higher levels to lower levels. Just like that, this diffusion makes an important contribution to electric current between drain and source of a MOSFET. Right? Between drain and source of a MOSFET, this diffusion also makes an important contribution. So, drain source current IDS. Have you listened that word? Drain to source current IDS. IDS is having a contribution not only from drifting but also from diffusion. Do you know what is drifting? Anybody? Drifting. D-R-I-F-T-I-N-G. Drifting means suddenly somebody says that there is a snake in the last bench. Right? Behind the last bench there is a 6-feet snake. What happens? Before everyone jumps out of the auditorium, I will jump first. Correct or not? Even the person who is holding the camera also, just holding the camera only, but lecturer is not there. Where the moment he listens the word, snake is there, he jumps. Then suddenly Mr. Leo stands there. Hey, don't go back. Till 3 o'clock he engaged you. You should not go back. But I am not leaving. And upon me, the students are falling. So everyone wants to go. Correct or not? A lot of collisions takes place. Correct or not? A very fat guy, very fat student, hits a lean student goes very fastly. And he hits another student. Yes? So what are these things? Collisions. What do you call them as? Collisions. Because of collisions, these people are moving from one place to another place. Correct or not? Yes? This is called as drifting. What do you call it as? So drifting is nothing but movement by collisions. Right? So movement by collisions and by diffusion both will contribute to IDS. So not only drifting, diffusion also, in addition to it, contributes to overall drain to source current. Imagine that all the individuals are electrons. Imagine that all the individuals including Mr. Kishore are electrons. So electrons are colliding one to another. That is why drift current will produce. Right? Average velocity of all the electrons, drift velocity, you call it as. Now what is the snake here? Because you told snake now in example. Sir, what is the snake, sir, here? There, what is the reason for running? Snake is reason for running. Here the reason for shifting of electrons is force, external force. What is the external force? Voltage, VDS, VGS, gate to source voltage, drain to source voltage. That is why biasing is required for a transistor to operate. Understand? Simply reading the statement in textbook, biasing is needed. Why biasing is needed? We don't know. Right? Now we have understood now why biasing is required. Without force we won't do. Without the examination timetable we don't start planning also. Yes? Correct or not? Without the ardent sitting before us we don't read. So we always habituated to force. By force only we are. Right? Afternoon class with no, please don't miss. The reason is, I will show you the difference between Indian education and Western education. I will show you the difference. What Newton has told us, applying force like this, then only displacement comes. Right? But that is false. That is false. Without applying force, you need to displace. That is what our ancestors have done. That is what Indian education system has taught to the people. Slowly I will take to the, suddenly if I say big things you won't digest, right? So first we see what is Newtonian dynamics. Newtonian dynamics is apply VGS, electrons will be passing through the drip space and it will give you ideas. Next. A baby is born. Now father and mother are speaking. What happens to this baby tomorrow? Tomorrow, this baby may become an engineer. Okay? In Maharashtra Engineering College. Some idea. Right? Tomorrow, this particular individual may study in Trichy. Something, some kind of discussion generally parents may know. Correct or not? Engineering, doctor, lawyer, like this. Like that, when IC technology was introduced, Gordon Murray has seen that vision. He got a vision. That vision is called as Murray's law. What is that vision? Murray's law. He thought like for every 18 months, the number of transistors that can be integrated will get doubled. That is his expectation. Everybody can have an expectation about their product. No. Yes, we have right to expect. So Gordon Murray also expected that this technology. I will tell you one interesting aspect. No law in the science and technology has met with this much accuracy than Murray's law by all the design engineers across the world. So Murray's law was met with greater accuracy. Till 2007, Murray's law's accuracy was very genuine, very exact. Okay? In 2007, there is a kind of translation, like Y2K bug. We also have got one bug in VLSI technology, where silicon is the raw material for all the products. Silicon, right? So with the silicon, that level of integration actually raises certain kind of problems. So people have shifted from silicon to other semiconductor compounds. So there is a shift. So this has been there on the past from long time onwards. But in 2007, people started manufacturing these integrated circuits more with semiconductor compounds than with the semiconductor material like silicon. There is a shift. Right? Why silicon is chosen? Why silicon is chosen? Anybody? What is the atomic number of silicon? 14. 1s2, 2s2, 2p6, 3s2, 3p2. Yes? So 2 plus 2 plus 6 plus 2 plus 2, 14. Valence electron contains how many? Valence orbit contains how many electrons? 4 electrons, tetravalent. So there is a possibility of combining with other materials, other elements, so that octet rule can be achieved. Right? Next. Yes. So he is Gordon Murray. Next one, please. Yeah. Yes. Yes. No exponential is forever. So transistors that are actually actually double in number when you use with this. From 1970, the first microprocessor 4004. What is the first microprocessor? 4004. And the journey goes on. We have Pentium 4. Afterwards, even we have 4 video processors. So new processors are emerging out. New processing technology is emerging out. Along with this, number of transistors. Initially, how many are there? Thousands. Now hundreds and hundreds. Right? Now millions of transistors we can accommodate in a given platform. Monolithic statue, we can say that. Ajanta, 4 days, 4 months, 4 years, 14 years. Any answer? 4 years? Please stand now. Appreciate it. Answer is 4 years. Very good. Intel takes a period of 4 years actually to bring out an IC as a product, a microprocessor as a product, right? So from planning, so that is the amount of time and effort that actually this company is taking out to bring a product. Yes. So before that gets switched on, let me tell you, what is the important part for VLSI? The basic component for VLSI product is transistor. What is that? Transistor. So transistor here means it is not BJT. Here we are talking about FET or MOSFET. FET, FET or MOSFET. MOSFET means what? Metal oxide, semiconductor, field effect, transistor. I changed the opinion of MOSFET. Right? Can anybody explain the operation of MOSFET here? Any points? MOSFET operation. Have you listened MOSFET? Yes? No, MOSFET operation. After listening to this example, you won't see like this. Next time you very... Now, you see this. I write these words vertically. Is a metal. What is O stands for? So here is an oxide. What is S stands for? Semiconductor. This is a field effect transistor. O. The structure of MOSFET. That's all. So you need not remember or look up the structure. Simply write the MOSFET vertically and yes. But the interesting aspect is what I am writing? Example of MOSFET is Indian family system. If you understand Indian family system, MOSFET operation is understood. Now what is this, sir? When I ask this question now, discuss about MOSFET operation, some of the basics are guilty. What is the operation? You listen to this example. In an Indian family, typical Indian family, now what is the setup we have? Father, mother, a daughter, a brother. We just keep these 4 characters. So we have son. Actually, son means brother. Brother always gives something to the daughter, right? Sister. That's what happens in Indian family. Even on Rakhi festival also, sister actually ties the Rakhi and brother gives something to her. Yes. So from brother side to daughter side or sister side, something always goes. Yes? And the control of the family is normally father. Okay. Abnormal cases I am not discussing. Normally, control of the family is by father. Right? If father is very angry, who will protect these children from father? Mother. You remember now? What is MOSFET now? The MOSFET is controlled by father. Which father? So gate controls the MOSFET operation. From where to where? Money flows, health flows, assistance flows, son to daughter. S for source, D for drain. So the electrons or the money or any kind of help travels from source to the drain, which is controlled by head of the family, A. And these two are protected from this by silicon dioxide mother. Understand now? You remember our family system, MOSFET operation is understood. Need not study any book. But whether it is available in any book? No. This won't be available. That is why the important information I want to tell you. No power, no internet, no video lecture will replace a live lecture by a good lecture. Right? Right? An interesting lecture. In the sense, if a lecturer is interested to teach a concept in the classroom, he is not in a position to be replaced by any kind of technology. This is what I want to say. So a lecturer in a classroom cannot be replaced by technology. Got my point? Because this is what lecturer can do to you where your technology may not be in a position to do. Robert can give you this example, MOSFET family. I don't think so unless otherwise you program it. Yes? So this is how we get, this is the best example of perception learning. What I told you before your tea break. Yes? So MOSFET family operation now you understand now? Please say last week. Tell me what is MOSFET operation by looking at the diagram. Make it fast. Yes, in Tamil or English? Anyway. How many terminals MOSFET is having?
8
Very good.
8 is a father.
Means what it does? Controls? Yes, correct. Source? Gives electrons. Very good. Dioxide, very good. It protects source and drain from official done. That's all. So no textbook is needed now, right? But in CMOS technology, how many transistors we are having? PMOS transistor. Just before 5 minutes I told one example. Mr. Leo sir is standing there. Mr. Kishore is running towards the window. He is stopping and saying that, sir, up to 3 o'clock you should be there. So this is what electrons are there. These electrons are there just by applying this VGS and VDS. What is VGS? Gate to source voltage. What is VDS? Drain to source voltage. These two voltages are applied consistently. So this happens in the case where VGS is gate to source voltage is greater than threshold voltage. For example, you are pushing a door. When you are pushing a door, a 2-year-old baby is pushing from the other side. Okay? Whether the door goes inside or it comes outside. Inside, because you are already well going to gym and all every day. So what happens when you push? So your force is more and 2-year-old baby force is less. So door opens. VGS is greater than VGS. Right? So if you are nothing but VGS, the 2-year-old baby is nothing but VGS. That means in a MOSFET there is a built-in potential. The built-in potential is called as threshold voltage. The minimum voltage that is required to turn on a device is called as threshold voltage. Understand? The minimum voltage that is required to apply externally so that the device gets turned on is called as threshold voltage. Now I will tell you one more instance where VGS is less than VTH. VGS is less than VTH means this side 2-year-old child is pushing, right? Other side I am standing and holding the door like this. Whether the door goes inside? No. Because the force from this side is very less. So VGS is less than. It may not happen in daily life. In the case of MOSFET, now once again the MOSFET conducts. Surprise, no? In day-to-day life, it is not happening, no? When the force is less from this side, it won't be opened up, right? But in MOSFET, it does. Right here, what is the speciality? I told you 10 minutes before that the total drain to source current is a combination of two phenomena. What is the phenomena? Drifting, diffusion. Okay. So in the earlier case, Vg is greater than Vth, drifting is acting along with the diffusion. But the importance of diffusion is undermined. But in the second case, drifting is not happening. Now which comes into picture? Diffusion comes into picture. Right? Even when Vg is less than Vth also, diffusion concept remains. That means there is small electric current that would be existing between drain to source, which will be microamperes. We call this current as sub-threshold current. What current it is? You can make a note of it. Normal electric current will be in milliamperes, sub-threshold current will be in microamperes. Sub-threshold current will happen or come into limelight when VGS is less than VTH, which you call it as weak inversion region. What do you call it as? Weak inversion region. When VGS is greater than VTH, strong inversion region. In strong inversion region, you will get drifting as well as diffusion. In weak inversion region, you have only diffusion. You don't have drifting. You understand this point? Shall you come with me again? Okay. VGS greater than VTH. IDS is because of two factors. What are they? Drifting and diffusion. When VGS less than VTH, although drifting stops, there is a concept because of which electric current would prevail. What is that concept? Diffusion. What is that concept? Got my point? So this is how the electron transport mechanism exists in a MOSFET. At your level, I try to explain. There are n number of factors are there, which I don't want to confuse you by saying all of them here. Right? So this is how basic MOSFET operation. Go with this slide. This particular CD is cut into pieces, and each one is called as an IC. You will get an IC out of it. Right? It is like CD-based structure. We call it as wafer. Now fabrication. I think in fabrication technology you might have studied this. And this wafer will be sliced, and we will get yield. Yield means the working ICs that will come out from a single wafer. It depends upon the area of a single IC. You call this IC as die, D-I-E. Die means working IC. Okay? So next. Fast actually comes into picture when the ICs are there which are having different defects. We have number of defects. Point defect, line defect, granular defect, defects are there. Okay? So by overcoming all the defects, application errors, how many ICs are in useful condition, based on which we calculate the yield value. YIEL. Next. And 2008 to 9 industry survey, nearly $2 to $3 billion of money industry is spending on only testing ICs, not fabrication, just for testing the load. Got my point? Next. Actually fabricated and do it. You call this region as deep submicron region, micrometers. This is something like deep submicron, or you even can conveniently say that nanometer region. Okay? So nanometer region means, so 65 nanometer, 90 nanometer, 130 nanometer. Now currently, FinFET is a transistor which has been fabricated using 27 nanometer technology. What is technology there? 27 nanometer technology. I need the help of two girls. Just please come. Nothing is applied, I am an electron. Here is the gate. So I will come here when VGS is applied. When VDS is applied, more positive voltage, I am coming towards it. This is what MOSFET operation. Right? Now, this space is called as drift space. What do you call it as? You please come closer. For example, earlier it is micrometer technology. Now it is 130 nanometer technology. Please come closer. Now 90 nanometer technology. Please come closer. Whether there is a possibility of any electron like me to pass here? Any possibility is there? Sir, you are not like electrons, are like elephant you are. Right? How you can pass here? Right? So what do you observe actually? Please, thanks sir. Akana, I have done this.
You are talking about technology in terms of micrometer and nanometer. It means that the length of the channel region reduces. Am I correct or not? The distance between the source and drain, you call it as length. So when they are coming closer, what is happening? The length of the channel region reduces. The length of the channel region reduces means it is an advancement or not? That's wrong. Now, if at all there is a chance, I can walk only less distance. Less distance means within no time I will finish this journey. Yes? That means time is less. Time is less means what? Speed is more. That means high speed circuits we can fabricate and the technology advances. Do you agree with me or not? Yes? High speed circuits we can actually fabricate when you reduce the length of the channel region. But these two students actually they hesitated to come still closer. Why? What's the reason? If you still come closer, there is no channel. Source and drain merges here. Correct or not? Then what is the end for this reduction in or scaling? What is the end for this scaling? There is no end now. If you go for scaling, keep on scaling, somewhere down the line, source and drain combines. Yes? So these are certain problems associated with the scaling. Particularly, noise emerges out when you scale down the devices. If the scaling is not done properly, scaling is nothing but reducing the length. Okay? Length is one factor. There are many other factors. Length is also one factor. When you reduce the length, noise arises out. What arises out? Noise comes out of the